for all A belongs to R. Okay, it's sigma algebra. So we show that this fancy, this cursive A, it contains each open subset of real line R. So for this, we need to show that it contains actually every bounded open interval of R. If it contains every bounded open interval of R, then it will contain each open set because it is sigma algebra, and every open set can be written as commutable disjoint union of bounded open intervals, and that must be cursive A because it's sigma algebra. So this one, it's in the cursive A. So now this one, it's in cursive A. So now you can see this minus infinity to B. It can be written as it's actually equal to the union and runs from 1 to infinity minus infinity and B minus 1 by n. You can say it's B minus 1 by n. Can I write this as is this are they equal? This set's equal. Let's choose any point here, a say x. So then it's actually they're actually equal. So let's try to verify this. Actually, it's very simple. You can do it yourself. So let's prove this. Without wasting of time, let's prove this. So let's choose any x here. Let x belongs to minus infinity to b, which implies minus infinity less than x less than b. So then I can choose n so large minus infinity less than x less than b minus 1 by n for some n. I can choose n so large such that x remains less than b minus 1 by n. So but this one, but it gives that x belongs to minus infinity b minus 1 by n, and which is subset of minus infinity b minus 1 by n closed interval ab. So whenever x belongs to this interval, it belongs to minus infinity b minus 1 by n closed for some n. So that means x belongs to the union. Okay. So this one, it is subset of the union, and converse is trivial because each minus infinity b minus 1 by n closed is subset of minus infinity to b. So therefore union is also subset of minus infinity to b. So which means the equality. They are equal actually. They are equal. So these sets are actually equal. So now look at this. It belongs to cursive A, and this minus infinity to b, it's a countable union of such sets. Each set is of this form. So that means it also belongs to cursive A. So if A is less than b, then the bounded open interval AB, it can be written as minus infinity to A intersection b to infinity. So sorry, it should be like this. A is less than b, A is here, b is here. So it's A to infinity minus infinity to b. It's minus infinity to b, then A to infinity. You can see the intersection of these two sets, and both the sets minus infinity to b, it belongs to cursive A, and A to infinity, it also belongs to cursive A, and cursive A is sigma algebra, so their intersection is also in cursive A. Let's see, it belongs to cursive A. So therefore cursive A is a sigma algebra containing every bounded open interval. So which implies therefore cursive A is a sigma algebra. Containing each bounded open interval. So in particular, it contains it means it contains every open subset actually. Now let let O be any open subset of R, then this O, it can be written as countable union of countable and disjoint union of bounded open intervals, and each bounded open interval it belongs to cursive A, and cursive A is sigma algebra, therefore their countable union is also in cursive A. It belongs to cursive A. So it belongs to cursive A. So now let's take any Borel set. Let B belongs to cursive B. It's a basic class of Borel subsets. It's a sigma algebra, smallest sigma algebra containing open sets, and this is also a sigma algebra containing open sets. This one is the smallest, so it's subset of actually cursive A. So which implies this Borel set, it belongs to cursive A. So that means, but what's the definition of cursive A? It means that F inverse of B is measurable. So that's 6. Inverse measure Borel set is measurable. Okay. Now we prove the last property. This 6 implies 1. Okay, 6 implies 1. So 6 means inverse measure Borel set is measurable, and 1 means F is measurable, means inverse measure open set is measurable. That's again obvious because every Borel set is measurable. So that's 6 implies 1. So assume that F inverse of B is measurable for each Borel subset B of R. It implies that F inverse of O is measurable for each open subset O of R as every open set is Borel set. As each open sets, as every open set is Borel set. Therefore, F inverse of open sets measurable for each open subset of R, which implies that F is measurable. So that implies that gives 6 implies 1. That's 1 actually. Yeah? F is measurable. So thank you.